Well, good morning, everybody. We'll go ahead and get started. Let me go ahead and open up in prayer, and I'll give you an idea of the things that we're going to be covering today. So, dear Heavenly Father, I pray that you would be working in the lives of each of the students in this course. I pray that the material that we'll be covering will be clear, and they can see how this is another nugget that's going to be helping them in their education as they're seeking to get the jobs that they would like to have in the future. Pray that you would bless their time in their experiences of getting a chance to study scripture, being able to derive the theological concepts we want to be pulling out of that, and give them interesting and creative ways for faith integration. And since this is the last time I'll be able to see these folks before Thanksgiving, I pray that there will be lots of things that they can be able to rejoice and be thankful for. In general, there's just so many things that we all have that we can be saying thank you. And so we just ask all these things in Jesus' name, we pray. Amen. Okay, so today there's going to be two things that I wanted to talk about. And so there's still a lot of content that we have installing, and it's always a judgment call how much to share and what to skip. And so sometimes that's a little bit difficult to manage. And then towards the last third or so, I'll go ahead and show another Arduino project. It's a different one than I was stating that I was going to show. I already had something assembled for a photodiode, and you'll get a chance to be seeing a little bit more about that. And since I think just about everybody has their Arduino kit up and running, and with the work that we did last Thursday, hopefully that's taking some of the mystique out. And so we're going through this section on the central processing unit. And as we've seen in other areas of what we focused on, there is a fair amount of optimization that goes on. This is an ongoing process of the vendors of trying to produce things that are meeting the needs of their customer base to make sure that they keep buying their products. And so we've been focusing on the Intel approach as well as the ARM approach, but there are legacy things that are related that we've got a chance to get some more insight into. And so we've been going through the reduced instruction set computers. And so there's yet some more details here that I wanted to have us to be thinking about here before we just completely put this chapter behind us. And so I'm going to try to think about some of the optimization that goes between the high-level language way that we are programming most of the time and how it starts to relate to things we would do at the assembly language, what we would do with compilers and stuff like that. And so that's the bent that I'm going to take for some of the focuses of what I'll be talking about here. So here's a little bit of motivation to that relationship between higher level language and how that impacts assembly. So this will be some information directly from the text. And so a variety of studies have been made to analyze the behavior of high-level language programs with the following general conclusion. There is a quite good agreement in the results of the mixture of language and applications. Assignment statements predominate, suggesting that the simple movement of data is of high importance. So data movement is something that needs to be thought through. And so we're seeing examples comparing various types of operations for Pascal and C. There's also a preponderance of conditional statements of if and loops, those types of things. These statements are implemented in machine language with some sort of compare and branch instruction. This suggests that the sequence control mechanism of the instruction set is important. So with these findings, this is trying to figure out, well, what is the biggest bang in terms of what should be done to try and improve the performance of compilers, maybe affecting what you would be doing with your computer architecture as you're thinking about your next version of your chips, or the way how a processor would fit into a larger computer architecture construct. So these results are instructive to the machine instruction set designer, indicating which types of statements occur most often and therefore should be supported in a quote optimal fashion. However, these results do not reveal which statements use the most time in the execution of the typical program. That is, we want to answer the question, given a compiled machine language program, which statements in the source language cause the execution of the most machine language instructions, and what is the execution time in these instructions? So there are various studies that Stalling refers to. And so what they've done is they analyzed a variety of measurements taken from compilers and programs for typesetting, computer-aided design, sorting, and file comparison. And so those are things that are out there that Stalling gets a chance to have us explore a little bit more. So I'm not going to continue just to highlight some of the things from the text, but at least wanted to be introducing that to give you a perspective. So much less work has been done on the occurrence of types of operands. Despite the importance of this topic, there are several aspects that are significant. And so here we're getting a chance to be seeing, well, what would an integer constant, a scalar variable, an array/structure, what it would be now, still thinking about for Pascal and C. So you can get some more insight from this by looking over some of the details in the text. But just to be continuing on, so what are the implications? A number of groups have looked at the results of these and have reported that and concluded that the attempt to make the instruction set architecture close to high-level language is not the most effective design strategy. So you just don't make the low-level language exactly like the high-level language. That's not going to be something that's going to produce the kind of results that you would want. Rather, the high-level languages can best be supported by optimizing performance of the most time-consuming features of typical high-level language programming. So we're starting to get a sense of like, well, what are the drivers? And so what are we going to go after to try and figure out how to improve the overall operations? So generalizing from the work of a number of researchers, three elements emerged that by and large characterize a RISC architecture. First, use a large number of registers or use a compiler to optimize register usage. So you want to be careful of how you're using registers. Registers are much better than memory. So this is intended to optimize operand referencing. The studies that just discussed show that there are several references per high-level language statement, and that there is a high proportion of move statements. This, coupled with locality and preponderance of scalar references, suggests that the performance can be improved by reducing memory references at the expense of more register references. So we get this dynamic tension. Should we change our basic processor modality to have more registers and then have less things that we go out to memory? And so that's the thing that is being brought up. Second, careful attention needs to be paid to the design of instruction pipelines. And so we've been starting to get into those details because of the high proportion of conditional branching and procedure calls instructions. A straightforward instruction pipeline will be ineffective. This manifests itself as a high proportion of instructions that are prefetched but never executed. And so we started to see some wiring diagrams when we were looking at this material that show you situations where you run into some problems. And finally, an instruction set consisting of high performance primitives is indicated. Instruction should have predictable cost that is measurable in execution time and code size, and increasing in energy dissipation, and be consistent with high performance implementations. And so those are just a couple other points that I wanted to make sure that we talked about. Okay, well, let me just jump forward now to a few other things, focusing on some of these optimization strategies and what has been done. One of the courses that I taught that was a lot of fun was the CS 160, and trying to think of some of the underlying things that start to come up with that class. One of the things that it touched on a little bit was graph theory. And so this is in this chapter that I wanted to talk about a little bit more and just give you a context on how Stalling was developing this. So the essence of an optimization task is to decide what quantities are to be assigned to registers at any given point in the program. So this technique most commonly is used in RISC compilers, is known as graph coloring, which is a technique borrowed from the discipline of topology. And so this originally wasn't colorized, and so I went ahead and put the coloring scheme here to maybe make this a little bit easier to see. The graph coloring problem is this: given a graph consisting of nodes and edges, assign colors to nodes such that the adjacent nodes have different colors, and do this in such a way as to minimize the number of different colors. So it's an optimization thing that we're looking at. The problem is adapted to compiler problem in the following way. First, the program is analyzed to build a register interface graph. The node of the graph are the symbolic registers. And so we have actual registers and symbolic registers that we're starting to think about, but ultimately it needs to be mapped to the actual registers. The nodes of the graph are the symbolic registers. If two symbolic registers are live during the same program fragment, then they are joined by one edge to depict interference. An attempt is then made to color the graph with n colors, where n is the number of registers. Nodes that share the same color can be assigned to the same register. If this process does not fully succeed, then those nodes that cannot be colored must be placed in memory, and loads and stores must be used to make space for the affected quantities when they are needed. So this is, we're trying to figure out how we're going to maximize the use of registers. We don't want to have any more than we need. And so right here, we're showing 3 registers being played out. So I'm not going to get into the details of topology and graph theory, but I'm just trying to give you, there's more going on under the hood, even more than what we have been talking about as we've been going through this material. So for SIS, we've noticed that a trend is to go towards richer instruction sets, which include larger numbers of instructions and more complex instructions. That's the distinguishing feature between RISC and CISC. 2 principal reasons have motivated this trend: a desire to simplify compilers and desire to improve performance. And so CISC processors have their strategy of how they think it would actually work. Underlying both of these reasons was the shift to high-level language on the part of programmers. Architects attempted to design machines that provide better support for high-level language. And so you can get a lot tighter mapping between a CISC type of a processor and the instruction sets and what you see in high-level language. So there is like a little bit of competition, if you will, thinking between, well, is the CISC solution the right way to go, or the RISC solution? And we've been trying to get a chance to be thinking about both of those and contrasting them again and again. We've already talked about some of this material, so I won't repeat it again, but just skip over it. So here is taken together, these characteristics can be asserted to determine the potential performance benefits of a RISC approach. A certain amount of circumstantial evidence can be presented. First, more effective optimizing compilers can be developed. With more primitive instructions, there are more opportunities for moving functions out of the loops, reorganizing code for efficiency, maximizing register utilization, and so on. It is even possible to compute parts of complex instructions at compile time. So those are some things that have been brought up that are out there. A second point is that most instructions generated by a compiler are relatively simple anyway. It would seem reasonable that a control unit built specifically for those instructions and using little or no microcode would execute them faster than a comparable CISC. And so we're trying to then still think between, well, should we do things in a CISC point of view or a RISC point of view? And a third point relates to the use of instruction pipelining. RISC researchers feel that the instruction pipeline technique can be applied much more effectively with a reduced instruction set. And so this is something that Stalling develops a little bit more in this chapter and some of the things that go beyond. So there is a little bit of dynamic tension going on between the RISC and the CISC approaches. That's stuff that's out there. Stalling also goes a lot broader in terms of characterization of multiple processors, and we are, for the most part, just focusing on the Intel and the ARM-based type of processors, but you can be looking at this table for a larger context. Here we started to introduce the effects of pipelining, and we got a chance to be thinking about, well, what would be, how would things improve if we have a two-stage pipeline, a three-stage pipeline, and we could start to do things in parallel? And so these are some of the results that we started to look at. So here are some other techniques that start to emerge. We can have a delayed branching, a delayed load, a loop unrolling. And so these are yet some other strategies that are there. Because of the simple and regular nature of RISC instructions, it is easier for hardware designers to implement a simple, fast pipeline. There are a few variations in instruction execution duration, and the pipeline can be tailored to reflect this. However, we have seen that data and branch dependencies reduce the overall execution rate. So everything looks great until you start to have looping or stuff like that. So to compensate for these dependencies, code reorganization techniques have been developed. And so these are three that are out there. So here just gives us an example of how we can start to manipulate how we're going to take the assembly instructions and reorder them such that can actually help improve the performance as a result. And so, do I really need to do this branch right now? We do need to do it, but maybe we fill in some other instructions to make this pipeline more full, and thus we can keep the overall operation better aligned. And so this is an illustration that's trying to show what that might look like. For loop unrolling, another compiler technique is to improve instruction parallelism is loop unrolling. And unrolling replicates the body of a loop some number of times, called the unrolling factor, and iterates by step U instead of one. And so we start to break things up into parts. And so this actually ends up performing better. And so that would be one of the things that may not be intuitive, that you can actually improve what you're going to get for your overall performance. So we have like our MIPS emulator. And so it actually, this was the second major part of our project work that we did. And so it's the MIPS R4000 is one of the first commercially available RISC chipsets that was developed by MIPS technology. And so this is the kind of a precursor for the things that we're looking for with an ARM processor. So I don't really need to get into the details of the instruction formats. But those are some things that you can read in more detail in Stalling. But let me just once again fast forward to a couple block diagrams that I wanted to finish up this discussion on. And so so there's multiple ways of how we can start to be doing some optimization and in a couple of different ways. This is another chart that shows you this a circular register. So this is a circular stack, And so we can have like three things that are related, and then that flows into another one, and then we can be doing those. And so we can just be using the resources in a more effective manner with a circular stack. Another thing that came up in this chapter that Stalling is talking about. So some of the major block diagrams that try and show some of the ways of how you can be optimizing a pipeline with some of the shortcomings that come up. Here is the first of two tables that Stalling uses that we can get a chance to get some insight into that. So in this section, Stalling looks at some of the enhancements to the pipeline illustrated in 1623. And so that is in the last chapter. We had a fairly simple rendering. And so to begin, we merge the instruction decode ID and operand fetch OF stages into a single ID stage, with the ID stage responsible for the instruction decode and register operation fetch. This is appropriate for a RISC machine, in which most operands are registers. It can also be used in CISC machines. In either case, memory operand fetch is deferred to the load store unit. And so we're getting a chance to see there's some thought of trying to figure out what we're going to be doing in a different way. So the figure shows the addition of the three enhancements: the instruction buffer, we have the store buffer, and we have the pre-decoder. So these are things that are shown in here, and having a couple of different ways that start to improve the performance. The instruction buffer supports the function of instruction prefetching. The object is to prevent or at least minimize delays in issuing instructions due to L1 instruction cache misses. Without instruction prefetching, when a cache miss occurs in the L1 instruction cache, the pipeline freezes until new instructions are brought from the L2 cache into the L1 cache. To counter this, the IF stage can fetch multiple instructions to keep the instruction buffer full. So this is what we're seeing as we're starting to, we're trying to keep that best case pipeline performance as best we can. So the precoder PD offloads some of the task of the instruction decoder and a stage to avoid the ID stage becoming a bottleneck. As previously discussed, the functions of the instruction decoder include decoding the opcode and operand fields and evaluating dependencies and hazards. So those are some other things that are laid out here. So another buffer, the store buffer, improves performance on store operations. In essence, the store buffer allows a load to bypass the completion of a store to access a memory location. Thus, the load instruction can make use of data items as soon as it is created, and does not have to wait for the data item to be stored in the data cache. So these are just a couple improvements that we see, and there is yet another version of this that starts to think about a few more items that can help this out even more. So we can have multiple reservation stations, we can have forwarding, we can have reorder buffering. These are all things that are laid out. And so maybe what we could do is just kind of go between this one and the previous slide, and we can see examples that there's more reservation stations. There's here we have a reordering buffer that we put in. And so these are, and now we're having like multiple pipelines that we can be, or multiple ways of how we can be doing things in parallel. That we saw that in the previous version. So my bottom point is I just wanted to point out a few more things in chapter 17 that there is some interesting development that has gone on with RISC computers. And the next thing that we'll focus on our next meeting, which will be a week from Tuesday, is we'll be thinking about instruction level parallelisms and superscalar processors. So let me see if there's any comments or questions on that. I know you guys are going through the whole textbook with the various quizzes that we're doing, but those are a few additional things that I wanted to make sure that were part of our discussion. Okay, well, let me go next to introduce something with our Arduino. And let me just query, Ryan, how are things going with your Arduino? Did you get it to communicate with your computer? I know you were talking about a USB 2 versus USB 3 issue. Okay, well, let's see what we can be doing to try and keep me in the loop for that, because that's actually an important thing. So let me make sure I'm sharing the right screen here. So stop sharing and then re-share my screen. So I'm going to introduce another project. And so last Tuesday, we had a simple push button type of project that would turn on an LED. And so there's a memory feature that we see. Now we get a chance to see another device. It's something called a photoresistor. And so basically this is it's like a 1 pixel detector. And so if you're taking a picture with your cell phone, it's gonna, there's like megapixels, whatever it is now, 10, 20, 40 megapixels that they have. This would be like 1 pixel that we get a chance to see how it's going to change what it's going to report as the light varies. And so there's this simple PDF that walks through this information. And so when I bought my first Arduino kit, this is the information that is shared. And so this is what a photo resistor looks like. And so it has some characteristics like a diode. But what it does is it's my wife and I, we also have solar system with our house. And so what it does, it actually receives that electricity, the electromagnetic energy from the sun, and converts it to electricity. So there's some relationship to what we're seeing here. And so the essence of what we have is we have like a resistor. And so here, a fixed resistor that's 10 kilo ohms. We're going to have a sampling point here that we're going to be interfacing with our Arduino. And then we have this photo cell. And remember when we were showing an LED, it had a triangle, and like the arrows were pointing out. Well, now we have that the arrows are pointing in. And so electromagnetic energy comes in here, actually is converted to a current. And so it's going to change what the voltage is going to be at this point, depending on the light level. So that's a little bit of perspective of what's going on. And so we have 2 versions of schematics that we're showing. So the first one is just a high level view of this. So this is showing the Arduino Uno. I know some of you have an Arduino Mega, so it would be slightly different. But we see this main connection here. This is a representation of what's the photoresistor, and this is the resistor. And so this is trying to show you this part of the circuit. But in addition, this is going to be leveraging some of the stuff we did last Thursday. We have a LED and a resistor. So we're using a 220 ohm resistor here. And so as the light that this is actually sensing changes, it's going to have an impact on what this LED will be showing. And so it will flicker, will get brighter or dimmer. And so those are some of the characteristics of what that would be like. Here is with our breadboard, what it would look like. And so this can be a nice shorthand to have you get something that is working. And you can also see that last week I actually put my Arduino actually on the breadboard. You don't have to do that. There are these same push-in pins that you can make these connections, and so that's what's being done in this situation. And so now we see specific pins laying out here, and so up here are the digital, down here are the analog, and then we have the power. We're using 5 volts, and then we also have ground that we need to supply to the circuit, and so ground is there. So that's the circuit that we have. And so I actually hooked this up to my my Surface, and so I have a remote desktop connection to that, and so this is the code that I'll be showing. And you can't see my my work area here, but what I'm doing right now is I'm putting my hand on top of the photoresistor, and you can see how it changed. And if I take it off, you can see that it very quickly goes back down to a lower level. So that's how I'm checking the photo resistor is working. And what I'll do in a few minutes, I'll actually zoom in on the setup, and you can see it actually working. So it'd be a little bit easier for me just to pull up a version of this with my laptop directly, but it's the same thing as what I have in the background. And so here are a couple things that we're seeing. And so we have the light. So we're defining some values here for pins. And so that's going to be pin 0. The LED is pin 11. The val is, we're initializing that to 0. We're defining the pin. And so this is the pin mode. We're defining it as an output. And that's going to be, and we're also going to be using the serial plotter. And so basically what we're doing is we're sending information to the serial plotter, and that's what you're seeing here. Just a little bit of light variation. There's clouds going, walking by in the sky, and so we're seeing a little bit of variation on the graph, and I just put my hand over that, and you can see that the percentage change, you can see it automatically changes its scale, that those things that I were seeing that were fairly large changes, we're seeing a lot larger swing when we just look at it like that. So thus we can see that we have a continual way of engaging with the Arduino, and that information is being fed back to my computer. And so I can have it a serial plotter showing that information. So we then have this value, we initialized it to 0. And so we have an analog read. And so once again, these are some of the commands that are embedded within the Arduino. So we do an analog read for this pin number 0. And so let me try and verify that I have it right. So Yeah, I didn't double check to make sure that my pins were right, so this may not be exactly the right number. So anyway, we have to do an analog read, and the thing that we need to be doing that analog read is for this point 0, this point here, A0. So let's go back to my circuit there again. And then after it does that read, it takes that value and it writes it to the LED. And this is the one that is coming out, and it's being passed to the serial plotter. You also know that there's a delay. And so it's a delay of 10 milliseconds or 0.0 seconds. And so this is in terms of milliseconds. And so that's where you can see like an order, a magnitude of 1,000 difference between that. So we can program a delay. I could make that longer if I wanted to. And so now we go to that serial port and we print that information out. And so those are the elements what we have here for that that script. So let me pull that back over so you can see it. And I'm not going through as much detail this time because I'm wanting to let you guys get a chance to try and be inspired. If anybody is interested in trying to do this one, I can walk you through in more detail. But I did share all the details from last Thursday that you can try. And so you can see how what it does is an automatic gain control. And so now it's cut that real high spikes are no longer here. And so now I'm really focusing on some low level signals. And so once again, if I put my hand over the LED, over the photoresistor, you can see how it just gets swamped out. And for a period of time, and I'd have to go back and check out I'm not sure how long this is, a couple of seconds, 20 seconds or so. Once this goes past, we'll see this go back. It's just going to auto scale back to this low level. So let me see if there's any comments or questions that folks have on what I shared.
For this project, you can just add it onto the Arduino, so you don't got to unplug stuff. You can just keep adding onto it.
Yeah, let me go back to the PDF. And give me a second, I'll move my setup here a little bit closer so you guys can see it. It's not going to look as nice as what we have in this picture, but so I'll stop sharing my screen. And get it close as I can without having it come unplugged. Can you guys see that okay? Is that
Yes.
something you can, okay. So you're not seeing the plotter at the moment, but I showed you the results of that. And so you can see now this LED, if I had like a meter, which is closer to what I was showing with the serial plotter, you can get an idea, get a better sense of its dynamic range. But I know the light is coming in this direction, so it changes a little bit as I do. If I take it off, it gets brighter. You can see that if I go. So that just gives you an idea. You don't need to have the serial plotter to get some feedback that it's working the way that you would like. I also have a video for this one that you guys can take a look at, and maybe it'll help inspire you with getting into some of the details with your Arduino kit. Any other comments or questions that people have on that? If not, I'll just go and continue on with a few points on the lecture side. And but I would highly recommend, if you haven't done it already, that you pull out your Arduino kit, use this time that we have on Thursday to get a chance to get a better sense of how these things work. And if you do have questions, please do reach out, and I'll be glad to see what I can do to clarify things. So the next chapter is we now get a chance to be thinking about instruction level parallelisms and superscalar processors. And so we've been introduced to the idea of parallelism. Now we're starting to get a chance to be thinking about how we can be optimizing those in various ways. And so this is the 1, 2, 3, 4, the third of 3 chapters that are focusing on the processor. And so now we'll get a chance to get introduced to superscalar versus super pipeline constraints. We'll be thinking about the design issues that come up, instruction level parallelism, machine parallelism, instruction issue policy, register renaming, branch prediction, superscalar execution, and superscalar implementation. We'll then start to get into, once again, mostly focusing on the ARM versus the Intel. And we'll first get a chance to be thinking a little bit more deeply about the Intel-based type of core architecture. And then we'll talk about 2 ARM processors, the Cortex A8 and the Cortex M3. And I believe the Raspberry Pi that I shared with you, I think it's a Cortex A8. And then you have something that's more higher performance that we can be seeing with an M3. So maybe that would be part of what we can be having in our discussion, is starting to have a shoot off, if you will, to see how one processor plays against another. I would say maybe at least half of you have an Intel-based processor in your laptop, with Apple going to Apple Silicon. That number may start to decrease. I already mentioned that Microsoft and other folks are also giving an option that you can either doing an Intel-based processor or use an ARM-based type of processor. So those are things that are available. So I'll just do maybe the first 3 slides here, and then I'll end the lecture. So the term superscalar refers to a machine that is designed to improve the performance of the execution of scalar instructions. In most applications, the bulk of the operations are on scalar quantities. Accordingly, the superscalar approach represents the next step in the evolution of high-performance general-purpose processors. And so we're starting to see like the 2nd and 3rd generation of like, well, if I wanted to go down a reduced instruction set path versus a CISC evolutionary path, what might some of those results be? And so we're getting a chance to be carrying both here a little bit, but I think some of this is going to be a little bit more in the sweet spot for the RISC. The essence of the superscalar approach is the ability to execute instructions independently and concurrently in different pipelines. The concept can be further exploited by allowing instructions to be executed in an order different from the program order. We started to see that in the last chapter, where we could start to break things up. And so just because you have a certain order, the way that you did your high-level language program, the compiler and some other things that are done underneath the hood may actually render those to try and improve performance. And so now we're getting introduced to a couple things, the scalar organization and the superscalar organization. So this figure, it compares in general terms of both of these. In traditional scalar organization, there is a single pipeline functional unit for integer operation and one for floating point operation. Parallelism is achieved by enabling multiple instructions to be at a different stage of the pipeline at one time. In the superscalar organization, there are multiple functional units, each of which is implemented as a pipeline. Each individual functional unit provides degree of parallelisms by virtue of the pipeline structure. The use of multiple functional units enables the processor to execute streams of instructions in parallel, one stream for each pipeline. It is the responsibility of the hardware to, in conjunction with the compiler, to assure that the parallel execution does not violate the intent of the program. So you can break things up. One analogy I like to be thinking about is TCP IP. If you see how things are actually go from point A to point B over the internet, it breaks it up into packets and they just send them all out. And then at the other end, it has to reassemble them in the right order. But it doesn't have to all go down exactly the same path when it's in the interim as it's starting to do that type of a function. So we'll leave it with here, but this figure provides an additional detail of a typical organization for a superscalar processor. So if you compare it with some of the things we saw in the last chapter, the L1 cache is divided into instruction and data. So that's a little bit different. Groups of instructions are fetched into an instruction buffer. The instruction decoder stage and falls at minimum, determining the opcode and operand specifiers. This stage also usually involves detection of inner instruction dependencies among the group of instructions that have been fetched but not yet dispatched. So you do one type of command, and it's typical that you have another type of command that would follow. These are things that it can be mindful of as starting to figure this out. So this stage selects instructions to be issued in the next instruction cycle and sends them to the issue window. The issue window holds all decoded instructions of issue in the next cycle. The width of the issue window corresponds to the degree of superscaling. And so we'll get a chance to, after the break, we'll get some specifics about different types of scaling approaches and how we can make things improve yet again in another way. And so that's going to be the focus after the break. And then we'll get a chance to be talking about the control unit and microprogramming control, the thing that Stalling highlights that's within the CPU, as well as maybe a fourth element in the von Neumann architecture. So we see things at a couple of levels starting to show up. Okay, with that, I'll stop sharing my screen. And let me just go around the virtual room, see if there's anything else that folks want us to make sure that we touch base before we call it a day. You can also just give me a thumbs up or raise your hand if you have something that you wanted to talk about, or if you want to just stay online, I'll talk with you one-on-one at the end. Anything else? Has everybody started? I know Ryan's still having some issues getting his connectivity going. And Ryan, if you want to stay on for a minute or two, I'll see if there's anything else I can offer up. Everybody else have your Arduino kit that you're starting to get things to work?
I'm starting to assemble mine, but the one quick question I have is the resistor I have is a 120, and it's saying
Okay.
on the PDF for 220. Does it really matter for the resistors or no?
Well, this is one of those interesting things. If you have a 120 ohms, and so I know for most, if not everybody, you haven't played with hardware. Some of you have. We have a couple engineers in our class. That's going to be like turning on the water spigot a little bit higher, so it's going to let more current in. So it probably would be okay, but another thing you could do, if it turns out that you just have 110 ohms, you can actually put two of them together and get 220. And so if you, just as long as you put them in series, it would work. And so, and if that's not quite clear to you, I'll just show this one figure again. And so let's just pretend for a moment that these are both resistors. And so for what you would say, David, this is a 110 ohm. If you put another one here, between this point and that point, you would get the equivalence of 220 ohms. So some of you all, the engineers will have to take circuits. And so you look at things, what happens in parallel versus what's in series. Resistors, if they're in series, you just add more to it. If you would put these in parallel, if I put a resistor here, that would actually reduce the amount of resistance that would be there. There's more paths for the electrons to take, and so it's going to be less resistance. And that's something you don't want to do in that situation. Okay. Thanks for the question, David. All right. Well, the Lord bless you guys. I'll look forward to seeing you a week. Let's see. Well, anyway, next week we're off, and then the following Tuesday, I'll look forward to seeing you all in class. Okay. God bless now.
Thank you. Have a good Thanksgiving.
Have a good
You
day,
too.
Professor.
Take care.
Happy Thanksgiving.
And then one more follow-up. Can I, with the resistors, I can do two of them, which is gonna be 240. Is it bad to have too much resistance?
That just means it's not going to be as bright. It's
Okay.
probably better to be a little bit on the side of having a little bit less than a little bit more.
Okay,
All right.
sounds good. Thank you. I'll start plugging it in now.
All right. Have fun, David.
All right, have a good Thanksgiving. Take care.
You too.
Thank you. Bye-bye.
Avery, just checking to see, do you have any questions? Anything I can help out with? Okay, well, I'm gonna assume that you're having some comm issues, so I'm apologize for that. God bless you. Have a good day.